Potential temperature. We've already seen that we can derive Poisson's equation for dry adiabatic motion in the atmosphere, where a parcel of air does not undergo phase changes and does not exchange heat with its environment. Poisson's equation is written as T equals T naught multiplied by P on P naught to the RD on CPD, where the subscript D indicates that these constants are for dry air. If we let P naught equals 1000 hectopascals, we can define the temperature as the potential temperature, theta, so that we can write theta equals T multiplied by P naught on P, where P naught is 1000 hectopascals, to the power of RD on CPD. P naught is, of 1000 hectopascals is taken as an approximate mean sea level pressure. So what this means is that if a parcel undergoes dry adiabatic motion with no phase changes, then theta is a conserved parameter. It is the temperature that a parcel has the potential to reach if it moves up or down to 1000 hectopascals. The implication of this, of course, is that parcels with different pressures can have the same potential temperature. So we've shown a case here where a parcel descends from P1 to P2 to 1000 hectopascals, and its temperature warms at each level to from T1 to T2 and then from T2 to theta, the potential temperature. But imagine a different parcel that starts at pressure P2 with the temperature T2, and that ascends to 1000 hectopascals. It will have the same potential temperature as the parcel that started at pressure P1 with temperature T1. So parcels with different temperatures can have the same potential temperature. And the potential temperature is a label for a parcel undergoing dry adiabatic motion. So, as noted already, parcels have the potential to reach T equals theta if moved dry adiabatically to P equals 1000 hectopascals. And so this value of potential temperature is a really useful label. And therefore, this dry adiabatic process is a very useful process to replicate on a Skew P log T aerological diagram. So we'll define formally the potential temperature as the temperature an air parcel would obtain if brought adiabatically to a pressure of 1000 hectopascals. Potential temperature is conserved for dry adiabatic motion, as shown here. And it also can be inverted to get a temperature at any pressure level, as shown in the form of the equation on the right hand side that's been rearranged. RD on CPD is 0.286. It ignores slight variations of CPD with temperature, and it ignores moisture. So it's purely dry adiabatic motion in this case. We'll extend that later on. So let's do a sample calculation. If a parcel's temperature at 850 hectopascals is 14 degrees Celsius, what's its potential temperature? Well, that's simply asking what's its temperature at 1000 hectopascals. So convert the temperature 14 degrees Celsius to Kelvin by adding 273.15, gives us 287.15 Kelvin. The initial pressure is 850 hectopascals, the final pressure is 1000 hectopascals, and so we write out Poisson's equation to get theta as shown there, and that gives us a temperature of 300.8 degrees Kelvin or 27.7 degrees Celsius. And so you might want to stop the video at this point, perform the calculation, and make sure I've done the right thing. So hopefully you got the same result. Finally, this is a screen grab of the Skew T-LogP aerological diagram. You can see the log pressure as straight lines, the isobars that run parallel. You can then see the isotherms that are skewed at 45 degrees, and then the green lines represent the lines of constant potential temperature. Now, because del Q is equal to 0, del Q divided by T is also equal to 0, which means that for processes that are dry adiabatic, they're also isentropic. So we can refer to the surfaces of constant potential temperature as isentropes. And as a parcel moves along these dry adiabats, you'll see that it cuts, say for example, as it ascends from 1000 hectopascals to 200 hectopascals shown, you'll see as it moves from effectively right to left on the diagram, it cuts across decreasing values of isotherms. In other words, it cools dry adiabatically. So the dry adiabat represents a rate of change of temperature of a parcel that's moving dry adiabatically.